Hello everybody. In this episode we are going to talk about this thing. Yes, it is Sputnik. Sputnik was the first artificial satellite circling the Earth. So it's about satellites that we are talking. So as I have mentioned, this one, Sputnik, was launched by the Russians in 1957, and it was about 60 centimeters in diameter and circled the Earth in an altitude of some 215 to 939 kilometers. So it was in a quite different altitude, so it had an ellipse, some to say, a shape of here the turn. Another satellite, so to say, is the ISS. We would not call it a satellite, but it is because it's circling the Earth, and everything circling the Earth is called a satellite. So, for example, also the Moon. But back to the ISS, it was launched 1998, and it is at an altitude of roughly 416 kilometers, so more or less same as Sputnik. The Moon, of course, is further away, 384,000 kilometers. One very special type of satellites we are gonna look at are the ones that we can see on the following picture, which is here. So what we see here is very close to the Earth. It is satellites and objects like Sputnik and ISS, sometimes also communication systems, military satellite, stuff like that. And there is here a very special place, as you can see. Of course, the satellites are drawn much too big here, but the distances are correct. And it is here just above the equator in this line. And these are called geostationary satellites. And they circle the Earth in an altitude of roughly 35,880 kilometers above the ground. So let's go to the theory of it. So if we have the Earth here and a satellite, then this satellite is going to move on a straight line if nothing happens. So with no gravity, it is just following this track. But with gravity, it is doing this circular path around the Earth. And therefore we can clearly see that it is the gravitational force, the gravity that is pulling the satellite to the inside towards the Earth and causing it to circle. So Fg supplies the force for the circular orbit. The circular orbit, of course, is the most simple one. It can be also an ellipse or even a hyperbola, but the circular one is just the one that we will look at. And as an equation, we can say that we have here this centripetal or radial force, which is here just gravity. So let's have a closer look at these geostationary satellites. So the geostationary satellites. I'll draw again the Earth. With the axis, so it turns around the axis. And I also draw here the equator. So the geostationary satellite are the ones that are stationary, as the name says. So maybe your uncle still has one of these satellite dishes on the roof to watch telly. And of course, this is pointing always to the same direction. So the satellite has to stay there. Otherwise, your grandmother has to go up to the roof and always follow the satellite. We don't want to do that. So therefore, in order to be stationary, it has to spin. And the time for one revolution of the Earth is 24 hours, as we all know. So the rotational duration has to be 24 hours as well. Of course, the same direction as the Earth. Now, can it circle above the North Pole, for example, in this type of manner? Then, of course, no, because the satellite is then spinning around like that, but the Earth is turning around like that. So the only way to turn is in this here area around here, or in this plane around the Earth. And it has to have a certain distance here in order to do that. So that's it. It has to be at the equator. So on the equator plane here. And it has to be in a certain altitude. So for the altitude, we can now just take this formula that we have seen up here. It's not really a formula, it's more something that is needed here. And we can just fill in what we have. Well, for the centripetal force, we have this m times r times omega squared. We could also write mv squared over r, but since we don't have v, the omega is more convenient here. And on the other hand, gravity g times m, that's the mass of the object that we have here. And the other mass is the mass of the Earth, and r squared. And r is the distance towards the center of the Earth. So this is r, while we'd call this the height above ground. The mass of the satellite drops, and we can just resolve it for r. So we take this r squared to the left hand side, so we get here r to the power of 3. And if you want r, then you have to take third root. And on the other side, g is left, mass of the Earth is left, and the omega goes down here squared, and omega is 2 pi over t, which has to be squared, so it is 2 pi squared over t squared, so the t squared I put up here. Here we go. And then we can put in the numbers, which is then 6.67 10 to the minus 11th Newton meter squared over kilogram squared. Mass of the Earth is 5.98 times 10 to the 24th kilogram. T is 24 hours times 3,600 seconds squared, and we have to divide that by 2 pi to the second, which is 4 times pi squared, and of course then third root out of that. So you can put that into your calculator to find out if this is true, and you should get an answer of 4.23 times 10 to the 7th meter, which is 42,300 kilometers. And if you want to have the height above ground, then we have to subtract the radius of the Earth. So therefore the height then is this r minus the radius of the Earth, which is 6,370 kilometers, 6.37 times 10 to the 6 meter, and this amounts to the 35,880 kilometers, or 3.588 times 10 to the 7th meter. So we can go back to the drawing, to this picture that we have seen here, and we can check and see that the drawing in fact looks quite okay. So we know the radius of the Earth is roughly 6,000 kilometers, so that's it. And then this is 6 times more, and yeah, that looks okay. So this line roughly 6 times more. Yeah, they have done a good job over there.